Otto cycle. So spark ignition engine. So Otto is the name of the person who said, let's describe the cycle in this way. It's got some underlying principles that he envisaged. We're going to introduce some terms. Just like half of you will be engine nuts and already know everything conceptual about engines. Half of you will be like me when I started uni. Like I went to a rural university where everyone wanted to be a mechanical engineer because mechanical engineers had things to do with engines, except for me. I didn't know anything about engines. So I have to kind of get everyone to the same kind of level. And then we're going to focus on the thermodynamic process. So I'll describe that in words. I'll put up some pictures. And we'll analyze the cycle. This one will be faster than an hour because I've pre-worked it. But Otto is a simple cycle. It's only a 4-process cycle. But I want to show you how to do a thermodynamic cycle analysis. So that's what I plan to do. That'll take us through to the end of the hour. Happy? Nah, it's fine. You can chip in. Jump in if I say something wrong. Seems likely. So, lots of you already know something about spark ignition engines. Here's some terms you're probably familiar with. Anyway, yes, I didn't know what this was until I studied thermodynamics. Anyway, I was young. You know, you guys are young. So I didn't know what a 2-litre engine was. I have a 2-litre Boxer engine in my Subaru. What does the 2-litre mean? It's not the amount of fuel it uses per cycle, because it can't be that. It's not the size of the tank, because that's, you know, cost me $60 to fill in, right? Is everyone comfortable with what displacement volume means? Is anyone not comfortable with what displacement volume means? Someone said 2.5-litre engine. Yeah. Cool, yeah, okay. So half a dozen, that's okay. So we'll talk about that, all right? It's the volume that the cylinders sweep out in the course of undertaking a cycle. Swept volume. All right, emissions, big deal. Emissions occur because we burn a fuel and we ideally create a carbon dioxide and water. Who has done stoichiometrics in chemistry? So who either did chemistry in high school, or you did the chem elective in first year, or you've some otherwise been exposed to, like how much oxygen do you need to burn this certain amount of fuel? A couple of people. Who is unfamiliar with that concept? That's fine. Good. I wasn't anyway. I didn't do well in chemistry in uni. Didn't study in high school. Compression ratio is another thing that you'll hear about. Compression ratios of 8, 12, 13, 14. What does that mean? Intake pressure, okay? So the idea that you're drawing in air from the atmosphere, what's the pressure in the cylinder at the start of the process, turbocharging and supercharging. Chris, would you like to describe the difference between turbocharging and supercharging?
One's pretty much engine driven, one's exhaust driven, really.
Good, that's fine. So for a turbocharger, you're taking energy out of the exhaust stream, because if you look at the tailpipe of a car, you've still got some heat there. You've potentially still got some pressure there. So I shouldn't say heat, should say temperature. So the idea is that you can extract out energy from the exhaust stream and compress the air coming in to the intake, and that will improve the performance of your engine. Supercharging is a little bit less, that's true. Supercharging is a little bit less tricky. It just drives a compressor off the shaft. So it takes mechanical work that would otherwise be going to the wheels and compresses the intaking air with it, and you get higher performing engines, as it were. So we can analyse those using our cycle. Peak power and torque at an RPM are typically the things that a manufacturer will specify. So they'll say 250 kilowatt at 11,000 RPM. No, that's obviously a motorbike. Sorry. There's potentially a rotary. We won't do rotary cycles, but you can in your assignment if you care to. So this is a typical question. Again, this is like we've gone from a quiz style question, right? Hopefully did some things in class, in lectures, and in PSSs that looked a little bit like things that you saw in quiz 1. This is an exam style question. So we've transitioned. We've gone into, this is where the course goes. And there's some things here we need to understand. An ideal Otto cycle has a compression ratio of 8. At the beginning of the compression process, air is at some pressure and temperature. So we're drawing in from atmosphere here, right? We're a little bit below atmospheric pressure. We're at atmospheric type temperatures. 750 kilojoules per kilogram of heat is transferred to the air during the constant volume heat addition process. Use the cold air assumption, so we should talk about that, and determine a bunch of things. Right, so we're going to work out the properties of all the different state points, and then the pressure and temperature at one of the state points. So that's just a read off the chart. Net work output, how much work are we getting out of the system? Right, thermal efficiency, like I said, at the end of undertaking a cycle analysis, we can develop thermal efficiency. And mean effective pressure is another term we should introduce and be aware of. Okay, so this is the question we're moving towards solving. Do a little bit of talking about the cycle, and then we'll go there. The Otto cycle is based on the idea of you've got a cylinder and you have 4 processes occur in the same cylinder separated by time. So one thing happens, then another thing happens, then another thing happens, all in the same space. That's different to for example, a turbine engine on an aircraft, okay, where you've got multiple different components, a compressor, a combustion chamber, a turbine, which are displaced by distance. They're in different places, and they all happen at the same time, okay? So this is a closed system. It's modeled as a closed system while the process is taking place. A gas turbine engine is modeled as a steady state open flow system. Steady state, steady flow open system. Valves are open and closed. I've got an animation of that. So they open and close at specific times to let air in or let air out. The spark quickly ignites the fuel. This is the difference between a spark ignition engine and a compression ignition engine. In a spark ignition engine, we assume that the fuel burns instantaneously. In reality, it doesn't, but it burns pretty fast. So the spark quickly ignites the fuel, and you get 1 power stroke for every 2 revolutions of the shaft. And it's common to use multiple cylinders as a shaft. This is something you're familiar with. 4-cylinder engine, 6-cylinder engine. And the idea there is, while one cylinder is firing with power, the other cylinder is exhausting or compressing. So you've got maybe 4 cylinders doing their 4 different processes, 1, then 1, then 1, then 1. Actually 1, then 3, then 2, then 4. But we will say, for our purposes, that this cycle is the air standard cycle. So we assume you get atmospheric air in, dry air, no humidity. We assume you get atmospheric air in at the intake, and you exhaust atmospheric air out the exhaust. That's not true, but it's close enough for our purposes. If you want to go into advanced analysis, you need to take into account the change of molecules and so forth, and you can do that in your assignment if you care to. You can do the stoichiometrics and so forth. So we say that the composition doesn't change. The Carnot cycle introduced us to the idea of adiabatic compression and adiabatic expansion, or used those. We use those in the Otto cycle as well. So we say that the heat transfer is minimal, so things happen fast. You can either insulate or you can do things fast to make them approach adiabatic. We do them fast. Combustion, again, spark ignites the heat really quickly, and the exhaust is considered to be instantaneous heat rejection. And in Carnot's cycle, he said, let's add heat isothermally. So let's compress the gas to a given temperature and then add heat as you expand things so that it's isothermal, okay? The Otto cycle, which is now a real cycle, okay, so we can actually do something with it, says it's not isothermal, but it's constant volume. So it's isochoric. And the reason we can model it as isochoric is because it happens quickly. The volume of the cylinder is changing all the time, right? Goes sinusoidal, right? And so you need to, at top dead center, you need to ignite the spark really quickly. At bottom dead center, you need to open the exhaust valve really quickly. Cool, this is an engine. I can look here. These are the 4 strokes if you're familiar with engines, a potential problem for you is that there's 4 strokes and there's 4 thermodynamic processes and they don't correlate. So the 4 thermodynamic processes happen only between 2 of the strokes. So what are we doing? So at the top here, I wonder if I can draw an animation without ruining it. Up at the top here, you've got valves. That's cool, right? And they are driven by cams. You should do cams in 2300, I think, next session. So the idea here is that you've got this shaft which is turning, and it's related to when this shaft turns. So you've got a timing belt joining the 2 of them, and as this eccentric cam, right, as it rotates around, it'll push on that valve and open it up, and then you'll have a spring, not shown, but the spring will be there. Right? You'll have a spring that will return the valve to its home position. Okay? So valves are controlling the flow in and out of the system. The valves are actually by a cam. The spark, bang, happens at top dead center. And then you've got this complicated mechanism which turns rectilinear motion, so up and down motion, into circular motion. And you can analyse the velocity of that using principles that you learn in 2300. Pretty much, you could spend your whole degree and get close to doing a car engine, pretty much. So thermodynamics would tell you how the energy works. 2300 and some of those courses would tell you about how the motion works and the accelerations, give you some of the forces and stresses and pressures. 3610 would give you heat transfers and so forth. So engines are very complicated. We will just deal with energy as in gross numbers as our first pass look at an engine. So we draw air in. What's that? The numbers come up. So 1, we draw in intake, close the valve, compress, ignite, power stroke, and then exhaust. Cool. It should be familiar. Some terms we use: top dead center. So I've already used this. Top dead center is when the cylinder is at its highest position in the standard orientation, right? I use a boxer, so it's a horizontally opposed engine, but still the top dead center is when the gas is at its most compressed position. Bottom dead center is then the opposite way, right? So when there's the most volume in the cylinder. Bore and stroke. Bore is the diameter of an engine, and stroke is the distance in millimeters between the top dead center and the bottom dead center. Displacement volume is then whatever volume is left at top dead center, whatever volume there is at bottom dead center minus whatever volume there is at top dead center. Okay, so when you talk about a 2-litre engine, maybe you've got a 4-cylinder, 2-litre engine. Each of the cylinders has half a litre of swept volume, right? And so each cylinder strokes through a cylinder of air that's half a litre in volume. This is a R1. You know, you find this on the internet, obviously. So it's got a bore and stroke. If you used pi d squared on 4 for the area, multiplied by height, which would be the stroke length, okay, that would give you 250 cc's, cubic centimetres, right? Because there's 4 cylinders and 4 of them must create a displacement volume of 1 litre. So that's displacement volume. That's how this is one of the typical ways you talk about engines. 2-litre engine, 2.5-litre engine. Clearance volume, so you don't compress the gas infinitely, you have some volume left at top dead center. And then you get a compression ratio, which is the volume at bottom dead center, so the maximum volume, divided by the volume at top dead center, the minimum volume. And so that's a ratio of, it's a volumetric ratio that says how much you're compressing the gas. And mean effective pressure is the average pressure that would create the same amount of power for that engine. So we're going to come back to mean effective pressure when we solve our problem. You either just learn lots about engines or nothing about engines at all. This is a pretty typical spec sheet, tells you stuff about the engine, displacement, bore and stroke, as I said, compression ratio, okay? So for this motorbike, I know what the swept volume is, and I know what the compression ratio is, so I know what the minimum volume is. I can calculate that. Gives me maximum power and maximum torque at an RPM. So they're figures we can use to analyse how efficient the engine is, and so forth. Right, Otto cycle. We should, so this is an analysis of the Otto cycle in the same way as I do the Carnot cycle. It should feel familiar. We'll do a couple of cycles in a similar manner. We'll go through it slower. Ask questions, because that slows me down. And then feedback from last year was, by the time you get to the 6th cycle, can we do it faster? So that's fine. So I'll try and slow it down now. And then by the time we're doing vapor compression refrigeration, I'll just go snap, snap, snap. You should know what these things are. But please ask questions. It slows me down. It's better for class understanding. So similar to the Carnot cycle, the first thing we do is we compress our gas, in this case. Then we have isochoric heat addition. Isochoric, not isothermal. So very quickly, we add heat. Then we have reversible adiabatic expansion. So do reversible expansion. And then we reject the heat. So we model the exhaust stroke because we assume that the composition of the gas changes. We assume we compress the gas, and then the gas mysteriously and instantaneously gets hot. And then we expand it, and then the gas instantaneously and mysteriously gets cold, because that allows us to treat it as a closed cycle. The isobaric exhaust and intake, so at the same pressure, atmospheric pressure, push the exhaust out and draw in new air, isn't considered in the Otto cycle. So this is what I'm saying. So the strokes don't align with the thermodynamic processes, because you've got two whole strokes that aren't considered in our cycle. So this is how that looks. This diagram's from Reisel, the textbook. So we get an intake, so our valve is open and air is coming in. Both valves close and the air is compressed. Then isochoric heat addition, so it's not a stroke, but it is a process. Right? So suddenly the gas gets very hot, and then we expand that, and then the exhaust and intake, well, yeah, so the exhaust on one end isn't a process, and the intake on the other end isn't a thermodynamic process. So that's that. What does it look like on a PV and TS diagram? Unfortunately, I chose to do the motorbike, so it's got a large compression ratio, so this looks a little bit thin, right? But we know, right, we've done isentropic expansion and compression before as single processes, so we know PV to the K equals some constant, okay, during the isentropic compression and expansion, right? And then at some volume equals some other number, and some volume equals some other number, we are adding heat, which means we must add pressure, right? So this is P, this is a PV diagram, right? Must add pressure, and here we're rejecting heat, so we must lose pressure, right? And that gives us our PV diagram. Our TS diagram for our Carnot, remember, was a rectangle, and that would indicate optimal, the best possible performance between two temperatures, okay? Here's our highest temperature, and here's our lowest temperature, and we can see it doesn't quite make a rectangle, but the area, anyway, I will explain why this is true later, okay? The area in here divided by the area of the outer rectangle is the second law efficiency of the cycle. So that's just how it works geometrically and on a graph. So it's something like that, but it's not perfect, because we don't have isothermal heat addition, right, which would be this line would be isothermal. We have isochoric heat addition, which is this line here. This is Reisel's treatment of the same thing. I think I agree with him that that line actually has a curve to it. I disagree. I think this line is much shorter than this line, but that's how he puts his ideal cycles. C, in this particular case, is a real PV chart, right? So you could use an encoder on the shaft to know where the shaft is, how far the shaft is rotated, and using some pretty simple maths, know what the volume is at the cylinder in that case, right? So that would give you where you are on this axis, and you could use a piezoelectric pressure sensor, and that would give you where you are on this axis, and as your engine fires, goes through its various cycles, you could plot a series of points on this PV chart, right? And that would tell you how your engine's actually performing. This is something that I think it was James Watt was doing to improve the efficiency of the initial steam engines. So he was saying, okay, well, and he was obviously doing it mechanically, right? He had a pen going up and down on the volume axis and then allowed pressure to go along, right? And so he was producing PV charts experimentally and saying, how can we get this more towards the ideal? So an actual track of the PV chart. How do we analyze these? Right? So all these processes take place as individual processes within a closed system, which we've already analysed. So you're already well versed with how this would happen. We start with our first law of thermodynamics for a closed system. Right? Up the top, we neglect kinetic energy and potential energy because they're typically very small influences on what we do. And we say Q minus W equals delta U. Right? The law of our first law for closed systems, disregarding kinetic and potential energies. Based on that, we know we've got adiabatic compression, so there's no heat. We know we've got isochoric heat addition and heat rejection, so there's no work, right? There's no boundary work when you have something that's an isochoric process. Real simple to analyse, okay? So we can get our work in the process from state points 1 to state point 2. We can get our heat from state points 2 to state point 3. We get our work from 3 to 4, and our heat from 4 to 1. Right? And interestingly, you can track this all out just based on the change in internal energy in the fluid. And then again, I've put exhaust and intake at the bottom. We don't consider them, but if you don't take them into account, you'll get twice the power that you should. So you only get 1 power stroke every 2 revolutions of the shaft. Our thermal efficiency for a Otto cycle, thermal efficiency is what you want to get out, work, and what you have to put in, Q, right? We've got 2 work terms. When we're compressing the gas, we put work into the system. Okay, so we have to start pushing something in, but when the gas is then expanding, when the cylinder is expanding, we get work out of the system. And we get more work out of the system than we have to put in to compress it. And this is again why you would set up cylinders on a shaft. You'd have one giving you power and the other one compressing for the next power stroke. And the residual, whatever's left over, is driving out the crankshaft and driving your gearbox. So work's what you want to get out, heat's what you have to get in. It's the sum of those 2 values, although one of them will be negative, the other one will be positive. So it's the difference between what you have to put in and what you get out. It is also 1 minus the heat in divided by the heat out. So that's a standard sort of thing. If Q equals CV delta T, and you assume constant specific heats, which you can do over small temperature ranges, it's not perfect over larger temperature ranges, then you can just take the temperatures, right? Your Q out becomes the difference in the temperatures, and your Q in becomes the difference in the temperatures. CV divides out on the top and bottom, right? You can take T1 divided by T2 out the front and you're starting to develop some ratios. These ratios come out of PV to the power of C, PV to the power of K equals a constant, right? So PV to the power of K is constant and PV on T, right? 2, 2, 2, 1, 1, 1, right? Between those two, why don't we draw down there? That's all right. Between those two, you can get these relationships here, all right? And we can define a thermal efficiency for an ideal Otto cycle. So this is assuming things like isobaric, things like isochoric, things like reversible, so isentropic compression and expansion, right? The efficiency for an ideal Otto cycle is 1 minus 1 on R is the compression ratio and K is the ratio of specific heats, which for air is 1.4, okay? And the reason this matters is because it tells you what you have to change to get a more efficient engine, right? So with Carnot, we said that the higher the hot space is and the colder the cold space is, the more efficient our heat engine. For the Otto cycle, by manipulating some ratios that we know, manipulating some properties that we know, we can say, well, the Carnot cycle's efficiency is based on two things. One is the compression ratio. A higher compression ratio makes this number smaller and makes the efficiency, thermal efficiency, closer to 1, okay? And a higher value for K makes this value bigger, all right? Which also brings you closer to 1 for your efficiency. The value for K is something we can't do a lot about if we're using air. It's pretty much fixed for us. If you want to use, what fluid has a high K value? That's fine. They have different K values. I think it's helium. Did diatomic have 1.667? Darn it. I shouldn't have asked a question I don't know the answer to. Anyone got the textbook? It's table A1 in the textbook anyway. There is a concept that you could use different fluids, so rather than using air, okay, yeah, diatomic, helium, monatomic, helium and argon, there you go, excellent. And diatomic would be, with 2 atoms would be hydrogen, yeah, there it is, 1.405. Yeah, so there is an idea that you could use a different gas, but you'd have to add heat differently. Combustion is just so convenient. 1.405 for H2. Yeah, I just looked it up. No, but helium and argon, being monatomic, are 1.667. So a small increase beyond 1 for K down here helps you with your efficiency. But what you can control is your compression ratio, right? So compression ratio, and we saw for the motorbike, it's up around 13. Compression ratio for a normal car. Who owns a car? I own a car. I didn't own a car when I was at uni for the first 5 years. I was at uni for a long time. Do you know the compression ratio of your car? 10? I'd give 10. I'd pay 10. Normally, it would be around the realm of 7 to 9 for just a stock standard petrol engine. And what limits that? So compression ratio improves thermal efficiency. What limits that is, in a normal spark ignition engine, you introduce the fuel into the air as it comes in, and then you compress it. You get a problem called auto ignition. So we know that as we compress a gas, the gas gets hotter. The more you compress it, right? If you up your compression ratio, then the gases get hotter and hotter. Then you get pre-ignition. So as you're in your compression stroke, without a spark, it ignites and tries to push back against the cylinder. So that's called engine knock, and you can use special fuels, notably high-octane fuels. Does anyone own a car that requires a high-octane fuel, where the manufacturer recommends, yep, there we go, to use whatever it is, 98, yeah. Cool, so that's trying to prevent engine knock by increasing the auto-ignition temperature and in some ways slowing down the process of ignition. The other thing we can do to change how much energy we get out of a single stroke is increase the amount of air, mass of air we have for the same displacement volume. So turbocharge or supercharge, increase the air pressure, M equals PV on RT, okay? So the colder your air coming in is, the more mass of air you have, and the higher the pressure of intake of air, the more mass of air you have for the same swept volume, assuming V is your constant here. You're not getting a larger engine, and so you can get more energy per cycle out of that. The problem if you compress air on the way in is you also compress and you increase temperature. Right, so in the process of compressing the air, you raise the temperature because that's what happens. And so you might do an intercooler. And you might have two turbochargers separated by an intercooler. So the idea is you compress the air, then you cool it down, and so it's nice and dense when you go in. Then you've got a lot of massive air, you can burn more massive fuel in the same space. So let's look at this cycle. So we've done, it may not feel like it, you might have to rest and digest on some of the stuff we've just been through, but we now know what we need to answer this question. Jump out a pen and a paper. I'll do it on OneNote, and we'll see how we go. And I was writing the final exam for this year, so I was reading through all the final exams from the years before. I think it was 2013, asked something like this for question 1. It was a smaller question of the 3 questions, but this was the kind of question that it asked. All right, so what are the things that we know? Let's do this. So if we draw a state table, 1, 2, 3, 4, and we want to track pressure, temperature, and specific volume. What do we know? At the beginning of the compression process, the air is 95 kPa, so that feels like there's a 95 there. I'm going to put my kPa there. 27 degrees C. Let's do degrees C. Okay. Because I can erase stuff really easy. 27 plus 273.15 is 300.15. Cooler. 450 kilojoules per kilogram. So, 750 is added here. So we're going to add some heat here, and we know how much heat we're going to add. And we're given the compression ratio. So we're not given the original volume, and that's okay. So we can just call this V1, but we know that V2, after the compression process, will be V1 divided by 8. We know that after the isochoric heat addition, so the volume doesn't change, between 2 and 3 will be V1 on 8. And we know that after the isentropic expansion, it will go back to V1. So if you're happy for me to use V1 as a variable, in this case I'm using specific volumes. It would be the same if they were absolute volumes, in this case because they're all just ratios anyway. And then the feeling is that we should be able to calculate the rest of the things in the process. All right. Excellent. Oh, there you go. We can calculate V1 from PV equals RT. V equals RT on P. So V1 equals RT1 on P1 equals 0.287 times 300.15 divided by 95. So we can actually work out what V1 is. We can't calculate the total volume because we don't know the displacement volume of the cylinder. All right. This solution process I introduced when I said, hey, let's talk about thermodynamic cycles at the beginning of the lecture, basically was fill out the state table and then use the values on the state table to answer the questions you're asked. There's some, if you get a little bit tricky, you're like, oh, I don't need to fill out all the state table. I only need these particular things. But for now, let's do the whole thing and think about getting more efficient as you get a little bit more experience with such things. And so the first thing we could do is calculate the pressure and temperature at state 2 based on a known compression ratio, right? So the problem I have is, if I zoom out, anyway, pressure 2 equals pressure 1, difference in volumes to the power of K, right? And that is from P1 V1 to the K equals P2 V2 to the K, because it's a closed process with an ideal gas, right? If you rearrange that, right, literally bring that V2 to the K over to the other side of the equation, right? You get that, which is 95. V1 on V2 is 8, irrespective of what V1 is, and K for air is 1.4. So the instruction we're given is use the cold air assumption. So this assumes the properties of air aren't changing as it changes in temperature. We'll refine that a little bit. There is a more advanced way of looking at air because the CV and the CP and the K do change as air gets hotter. But for now, we'll just make the analysis simple. All right. And that will give us a pressure 2 of 1745.01. So that's our pressure 2. Now, our temperature 2 equals temperature 1 times P2 V2 on P1 V1, right? And that's from PV on T equals our combined gas law. Okay, so we've just rearranged the combined gas law to give us an equation that's going to help us to solve our temperatures. And so our T2 is 689.164 Kelvin. So now I'm going to come back to my table. Oops. Excellent. 689 and 174. All right, I'm not going to fill out temperature in centigrade unless I was particularly asked for that temperature. So that gives us our state point 2. Okay, so we're just going through the cycle. State point 2, state point 3, we're given our heat addition. Okay, so our temperature 3 must equal whatever our temperature 2 was, plus our change in temperature. And our change in temperature must be our CV Q divided by CV. Sorry. Q equals, well, lowercase q equals CV delta T. So therefore, delta T equals Q divided by CV. Happy with that? If I do something grossly incorrect, pull me up on it. If I do something a little bit incorrect, pull me up on it. So 689.1 plus 750 divided by 0.718 kilojoules per kilogram. This would be kilojoules per kilogram Kelvin. That's Kelvin. And I get 1733.73 Kelvin. So that's our temperature at state point 3. Right, fill out my table. Pressure, I can calculate using the combined gas law, right? So it's PV on T equals PV on T, and my pressure for 3 is 438, let's call it 4390 kPa. I'm just speeding up a little bit because I want to get this solution out. And then similarly, temperature and pressure for state point 4. So I've got 239 and 755. Okay, so that's pretty typical. You do some maths. So for an ideal gas problem, you use the ideal gas equations of state and you manipulate them and fill out your table. For a pure substances question, you often look up your tables and do some interpolation to fill out your state table. And so now we know the pressure, the temperature in Kelvin, and the specific volume of the gas at each of the state points. And now we're asked, determine the pressure and temperature at the end of the heat addition process. Okay, so the end of the heat addition process is state point 3, and they are just read from the table problems. So pressure is 4390 kPa, and temperature is 1734 Kelvin. Excellent. The net work output is however much work we have to put in, well, however much work we get out minus however much work we get in. So B work net equals work out minus work in. Work out we know to be our difference in, because, right, so from Q minus W equals delta U, all right, during our processes that do work, Q's 0, so our W is just our delta U, right, and delta U is just CV delta T, right, and so our work net we can just say is CV, and work out is the expansion process between 4 and 3, so it's temperature 4 minus temperature 3. Work in is temperature 2 minus temperature 1 minus 300, right? Substitute those values in and you'll get the work being 423.35. Interestingly, a different way that we could have done work is to say that work net must be equal to Q net, which is 750 minus, because 750 was our Q in, we were given that, 750 minus the heat rejection from process step 4 to process step 1. So minus CV 755 minus 300. And you find that also equals, that should be kilojoules per kilogram. We'll get 423.35 kilojoules per kilogram. So there's a few different ways of calculating that. I think the second one's simpler. You can find work just by knowing heat. C, the thermal efficiency, is what you got out of the system divided by what you had to put into it. So thermal efficiency is work net divided by Q in. We've got our work net at 423. 423 divided by 750 was our defined Q in, right? And that gets you 56.5%. Interestingly, you get the same value if you just say 1 minus 1 divided by R to the K minus 1. So if you substitute the compression ratio 8 and K of 1.4 into that, you get 56.5%. So it just shows the equivalence of those things. So we've analysed the whole cycle and just come up with the same thing. The second law of efficiency, although not asked for in the question, can be calculated. And let's leave it there except to say, there's all the calcs. I'll upload the PowerPoint slides. You now possibly know more about engines than you did on the way in. That's what we covered.